Hi, I'm Martin Archer and I am a UKRI Stephen Hawking Fellow in Space Physics and Public Engagement at Imperial College London in the UK. And I'm going to talk about hearing the invisible, the versatility of sound in engaging. Now, in my field, much of what we do is actually invisible. The journey starts off at the sun, which we know is visible. This is actually a picture of the sun taken in ultraviolet wavelengths. And it might end up at the top of the atmosphere with processes like the Northern Lights or Aurora Borealis, which again is visible. But most of the stuff in between is completely invisible. We cannot remote sense it. And so our field heavily relies on in situ spacecraft observations, which often come in the form of time series, like you can see here. This is the magnetic field observed at geostationary orbit, which you can see has lots of oscillations and waves present. So this is how we do our science, but when it comes to engaging, a time series, unfortunately, is somewhat boring. And that means that we can't rely on visually arresting images in the same way that many fields of astronomy can. However, we can use sound. It's the most relevant sense when it comes to a time series like this. It can actually be really powerful. Our sense of hearing is amazing. It's non-linear. It can pick out things and separate sources in ways that standard Fourier techniques and visually identifying things just simply cannot. But when it comes on the engagement side, our sense of hearing is innate. It can make things accessible. It can make our science palpable. And as I'm going to talk about in this presentation, it's incredibly versatile as a medium. How do we actually do this sonification though? Well, one of the easiest ways is this thing called Orification, and it's literally just a one-to-one mapping of your data samples to audio samples. And so you're retaining all of the information, nothing is being changed. The only thing you're changing is the sampling frequency and the gain. For instance, the waves that I study are in the ultra low frequency range. And so by translating that into audible frequencies, that massively speeds up our data into something that sounds like this. And that was about 4 days that you listened to there in about 4 seconds. Now, the reason why I like Orification is it means you're not imposing your own aesthetics on the data. It is truly what the data is. It's a perfect representation of that data, and it means you're not losing any information. And therefore, you can solicit comments on what people feel about the data itself rather than something that you might have imposed a whole load of things on yourself. And that's what you can see on the right-hand side. A whole load of comments from SoundCloud of what people think the space around our planet sounds like. Now, sometimes Orification's not going to cut it because a lot of the waves in space have very well-defined frequencies, but only for a handful of oscillations, which is not something that we are used to hearing here on Earth, where we might have hundreds to thousands of oscillations like in a musical instrument. And so we need different techniques to be able to tease out that, and time stretching is something that is really good. You can have exactly the same power spectrum, but all you do is change the number of oscillations present. And so I'm detailing here what's called a wavelet phase vocoder. That's just one reversible technique that can time stretch your data from something on the top, which if you were to turn into audio would sound like this, literally just a thud, into something that sounds like this. So you can hear that it's going on for longer, and you can start to hear its pitch. So how can we actually use these results? Well, one of the most obvious things is that we can use sonification to communicate the results of our research, which is something I've done in a number of different examples. This one particularly here was the recording of the foreshock region, so just outside of Earth's magnetosphere, what that sounds like normally, comparing that to solar storm conditions. So this is what you'd normally expect to observe under regular solar wind. And then in a paper by Lucille Turk and collaborators, which I was a co-author on, we showed that during solar storm conditions, you got a very different set of waves, which can be communicated perfectly just through sonification without having to explain it in words, which might be more complicated. And this was used as the basis of a press release for the European Space Agency. Another technique that we can use is soundscapes, part of an immersive sort of experience. So this was a soundscape for young families where they listened to the sounds whilst going on a bit of a journey, and we took their thoughts from beforehand to afterwards about what they thought space was like in graffiti walls. And you can see the words really did change from before to after. And teasing out some of the themes present, we were showing that actually they really did get a grasp of some of the underlying physics present, literally just by listening to the data, not by having somebody explain it to them. They were able to grasp some of these concepts themselves just through the sound. And this was just written up recently this year in Geoscience Communication. A third way we can use this sounds are in the creation of art, and not just art in the communication of science, but art for art's sake. I want to play you this trailer.
Still to come, reports of widespread disturbances in technology.
How to get from A to B or 2 to 3 in the most direct route possible, without getting lost or forgetting the purpose of the journey.
5, 4. The engine's now building up to 7.7 million pounds of thrust. All engines running.
So if you want to know more about this project that saw creative films based around the sounds of space, go to events all around the world. I have a poster in this CAP 2021, or I have a paper that came out last year in Geoscience Communication. The last way I want to talk about is exploratory citizen science, because we're making a representation of our data far more accessible, reducing the barrier to entry to explore it and analyze it. And that's exactly what we've been doing with school students, getting them to listen to these sounds and find events for us. And one group was able to find this. This really stood out to them. It didn't sound like any of the other sounds present, and it turned out that they were the unexpected sounds that follow a solar storm at geostationary orbit. So I want to just conclude this talk by saying that sound is a really powerful tool that you can use in so many different ways in your engagement practice. Some of the next steps that I'm going to be using sound in as part of my fellowship is by taking, rather than satellite observations, entire 3D simulations, and through machine learning, turning that into a way that people can engage in it in an interactive way, such as through a magnetospheric drum kit, but also in the creation of music and through workshops with community groups and what have you. So what I want to say is, don't forget about sound when it comes to your engagement. And if you have any other questions, please feel free to drop me an email. Thank you.